Welcome back to the show, everyone. Today, we're diving into the world of automotive technology, specifically exploring how to make those fancy surround view systems even better. Joining me is lead researcher's name, a leading researcher in computer vision, and field expert's name, a renowned expert in automotive engineering. Thank you for joining us.
It's a pleasure to be here.
And we're thrilled to have your expertise on the show. Thank you for having me. I'm excited to discuss this research. Let's start with the problem you're addressing in this paper. What's the issue with surround view systems as they stand now?
Well, surround view systems stitch together images from multiple cameras to give the driver a bird's eye view around the car. But because each camera has its own auto white balance, AWB, and global tone mapping, GTM settings, the colors and brightness levels can be quite different. This leads to noticeable seams and color discrepancies in the stitched image, which can be distracting and even hinder the driver's perception of the surroundings.
That makes sense. It's like trying to put together a jigsaw puzzle where the pieces aren't quite the same shade. How important is this issue in terms of user experience and the overall advancement of automotive technology? It's a critical issue, especially as we move towards autonomous driving. A clear and accurate surround view is essential for driver assistance systems and self-driving algorithms to make informed decisions. Distorted or inconsistent colors can confuse these systems and lead to errors. Excellent points. So, researcher's name, tell us about the solution you propose in the paper. How do you address these color inconsistencies?
Our solution leverages the metadata information already generated by the camera's image signal processor, ISP. This metadata includes the AWB and GTM settings applied to each camera image. We use this metadata to harmonize the colors and brightness levels before stitching the images together.
Can you elaborate on how you use this metadata? I'm not quite sure I understand how it can be used to correct the colors.
Imagine each camera has its own unique color filter or a dial that adjusts the brightness. The metadata essentially tells us the settings of these filters for each camera. Instead of applying a single global color correction, we use a blending approach. We apply a smooth curve, what we call a logistic function, to gradually blend the AWB and GTM settings of adjacent cameras. This way, we smoothly transition from one camera's color and brightness to the next, creating a seamless visual experience.
So it's like blending the colors in a gradient rather than just abruptly changing them from one camera to the next. That's a fascinating approach.
Exactly. And it's not just a matter of aesthetic improvement. It also ensures that the color information is consistent for the driver assistance systems and algorithms, making the surround view system more reliable.
What are your thoughts on this approach? How does it compare to other color harmonization techniques? This method is quite innovative and addresses the key limitations of traditional color transfer methods, like those that rely on selecting a reference image or computing color statistics from overlapping regions. Those approaches often struggle with scene variations and can be computationally intensive. The metadata-based approach is more efficient and robust, making it ideal for real-time applications like surround view systems. That's an important point. Let's move on to the results of your research. What were the key findings?
Our experiments show that the metadata-based harmonization method significantly outperforms the traditional patch-based global color transfer (GCT) method in both visual quality and runtime. The stitched images using our approach have a much smoother color and brightness transition between adjacent cameras, leading to a more natural and pleasant viewing experience for the driver.
And what about the runtime performance? That's crucial for real-time applications like surround view systems.
Our method achieved a significant runtime improvement, reducing the computational cost by 50% compared to the GCT method. This is because we directly utilize the metadata information, eliminating the need for computationally expensive color statistics calculations.
So it's a win-win situation. Better visual quality and faster processing. That's quite impressive. How significant are these improvements for the automotive industry? These advancements are crucial. They pave the way for more accurate and reliable surround view systems, which are essential for advanced driver assistance systems and ultimately autonomous driving. As autonomous vehicles become more prevalent, the need for precise and robust perception systems will only increase. This research makes a significant contribution towards achieving that goal. That's a great point. Are there any limitations to your approach that you'd like to highlight?
One limitation is the dataset we used for evaluation. It's not a comprehensive benchmark for multi-camera harmonization. We're currently working on expanding the dataset to include more diverse scenarios and lighting conditions. Also, while our method works well with current ISP metadata, there might be room for improvement by exploring different blending curves and even incorporating additional metadata from the ISP.
Those are valid points. Are there any other challenges or limitations that come to mind in terms of multi-camera processing for automotive applications? Certainly. One challenge is the synchronization of multiple cameras. Ensuring that all cameras are capturing images at the same time is crucial for accurate stitching. Another challenge is dealing with dynamic scenes. Objects moving in the field of view can introduce distortions and require more sophisticated algorithms for image alignment and harmonization. Thank you for pointing that out. Where do you see this research heading in the future?
We're exploring ways to improve the blending curves and potentially incorporate more metadata information from the ISP. We're also investigating how to adapt our approach for different camera configurations and sensor types, as well as how to address the challenge of dynamic scenes. Ultimately, our goal is to develop a truly robust and reliable color harmonization method for surround view systems that can seamlessly integrate with advanced driver assistance systems and ultimately contribute to the development of safer and more efficient autonomous vehicles.
That sounds incredibly promising. Do you have any final thoughts on the implications of this research for the automotive industry? I believe this research highlights the importance of focusing on the fine details, even within seemingly complex systems. Achieving seamless and accurate visual perception is crucial for the success of autonomous vehicles, and this paper presents a significant step forward in that direction. It's a reminder that the success of self-driving technology relies not just on sophisticated algorithms, but also on addressing these seemingly smaller, yet critically important details like color harmonization. Well said. Thank you both for joining us today and sharing your insights on this fascinating research. It's clear that color harmonization is a key element in the development of advanced automotive technologies, and your work is making a real difference in pushing the boundaries of what's possible.